Well, welcome back once again. Here we are at the third kill simulation. This is one of my favorite lectures to do. I've been doing this for a few years. And in this situation, we are modeling the large laboratory kill in my university laboratory. And this kill is known as the Swindell kill because Swindell Dressler donated it to our laboratory for our use. So we're going to get about the business of doing this simulation. Before I get started, I want to say that it's always possible that I've made an arithmetic mistake. Since I'm not using Excel and I'm having to do these additions manually, I apologize in advance if I have made a mistake. But nevertheless, I've done the best I could to make things as accurate as possible. Okay, well, in the other two simulations and in this unit of the course, we've always said the total heat required equals the heat required by the load. We have to heat up the load to the centering temperature, plus we have to add in the furnace heat storage, plus we have to add in the furnace heat losses. And there are several places that we can have heat losses, of course. So that's the statement of the law of conservation of energy. It's just a simple energy balance. Today, we're also going to look at the fuel requirement, and that's going to be determined from the total predicted heat required in our simulation. So here we go. So the problem is to find the total heat requirement per cycle in this process. And in this process, you're going to find out that we're going to be heating 500 clay bricks, green clay bricks that have a little moisture content. We're going to heat them up to 2000 degrees Fahrenheit from an ambient temperature of 60 degrees Fahrenheit. We're going to heat them up in 8 hours. Once we get to 2000 degrees Fahrenheit, we're going to soak for 5 hours. Then we're going to cut the kiln off. No more gas consumed after that point. The combustion is supposed to be at 10% excess air. That certainly will be true, as you will see, for the soak, but maybe will vary a bit in the preheat based on the limitations of this steady state heat flow model we have in E-Solutions. The chamber dimensions are a width of 3.83 feet, a length of 6.75 feet. That's going into the kiln, the length, 3.83 feet across the kiln, and the height of the kiln is, again, 6.75 feet. So all these dimensions are in inch-pound units. Our simulation could be done, of course, in metric units. Now you can see the refractory insulation. When we received this kiln, insulation consisted of ceramic modules. You can see them looking like big blocks attached to the shell of the kiln, the sidewalls, the end wall, the sidewall again, and you can't see the crown, but that's what's up there. They're suspended from the roof or crown of the furnace. The insulation in the original design of this kiln was a castable bottom, and there were beams and tile where the load was set on. So you can see those, and here's a little information on the thickness of the insulations. We're going to assume no flue. We know this kiln has a flue, but we assume no flue for the purpose of this simulation. Now, in terms of the internals in the kiln furniture, as you might call it, or structural parts, there are 15 of these beams, I-beams, okay, refractory ceramic I-beams. There are 12 of these deck blocks that span across the beams, allow air circulation underneath the tile for more even heating. And then there are 24 skewback brick, and you can see the skewback right here. And what the skewback is doing is providing a solid wearing surface, a durable surface where the kill car can be pushed into the kill without damaging the refractory fiber. So these skewback bricks are right here, and they go around the kill wherever the kill car would potentially contact the kill. Now, this kill design has been modified later in its life with a fiber deck with silicon carbide post and tile used to fire loads in the kill. But right now, we're modeling the original installation configuration in the kill. The working load in the kill is going to be 500 clay bricks. In their wet condition, they're 4.35 pounds each, and they are at 0.5%, 0.5% moisture on a wet weight basis. So one of the challenges in firing this is going to be keeping up with the weight of the bricks as we go through the firing cycle, because you're going to find out that they get lighter as we go along. Now, some material facts. The heat of vaporization of water is 2263 joules per gram. Specific heat of clay and refractory is 0.2 calories per gram per degree Celsius, which is the same as 0.2 BTUs per pound per degree Fahrenheit. And we took the reactions on heating the clay from a simultaneous thermal analysis experiment in the lab. We took the clay and we heated it, and here's the thermogravimetric scale, and the the green line is the thermogravimetric line, and you can see that when we get up here in the realm of almost 500 degrees Fahrenheit, we start losing weight. And we've got a total weight loss of 12.7%. Now, of course, that's the dehydroxylation of the clay, removal of what we call the chemically combined water, or hydroxyls come singing out of the clay crystals, and they immediately combine with hydrogen to put water vapor into the kill exhaust. Now, we can measure that endothermic reaction here with this particular lab instrument, and you can see that the area under the curve is 552 joules per gram. I hope I read that correctly to you. So there's an endothermic reaction on heating. That's the dehydroxylation. And this is kaolin, and as is typical of kaolins, it's going to go through a mullite formation, primary mullite formation, and it does up here, and we can measure the exothermic reaction due to the formation of the mullite. We're going to assume the formation of the mullite is exactly at 1050 degrees Celsius, even though you could see on heating it occurred over a little period of time. The firing temperature of the furnace at 2000 degrees Fahrenheit or 1093 degrees C is shown by this dotted line. So certainly the weight loss occurs in the firing cycle. The endothermic reaction occurs in the firing cycle, and the exothermic reaction forming mullite is seen in this firing cycle. Now, other clays that don't contain as much alumina as kaolin will show perhaps a little less in the endothermic reaction and a substantial amount less in the exothermic reaction, since at lower alumina content, typically 17 to 20% or about, in most alumina and most earthenware objects, we don't have that much mullite form, but some. So we're basing our material information on laboratory instruments that we measured in our own laboratory. And so now I presented a chart of things that happen on heating up. This is in degrees Fahrenheit with degrees Celsius in parentheses. So the first thing that happens on heating is we heat the bricks up to the boiling point of water. And we start out with their wet weight, 4.35 pounds. And we're going to evaporate that water that was there, 0.02 pounds of water. Okay. Then we're going to heat up the bricks to dehydroxylation using the dry weight of the bricks. We're going to use the dry weight of the bricks because the dehydroxylation energy is in BTUs per pound of that material. Then we're going to heat up the bricks to their maturing temperature, 2000 degrees. We've temporarily ignored the exothermic reaction of forming mullite. It was just easier to put one thing here in this particular row. That's the energy to heat up to the final temperature. But then we're going to come back and pick up the exothermic reaction, which is going to be a negative amount of energy in terms of BTUs per pound there because of the formation of the mullite. So we've tried to keep up with this, and it might be useful for you to pause the presentation and print this so you can keep up with things. In the next slide, we've a similar chart. It has all the energy that we had before in the previous chart, but here we are computing the energy for each increment of temperature or each event, like the evaporation of the water. That's the energy required. Heating up the bricks up to dehydroxylation, 717 BTUs per brick. Okay, continuing on for dehydroxylation, it took 1080 BTUs per brick to cause dehydroxylation to take place. Then heating up to the final temperature, 726 BTUs. When we got up and accounted for the exothermic reaction, we get some energy back in our process, 249 BTUs. So we can add all these up and get a net amount of energy required in firing the brick. So when you compute that, you're going to come up to 872 BTUs per pound on a fired weight basis. Now let's just think about that number for a minute. There are a lot of people who've calculated the theoretical energy to fire a brick. It depends on the particular raw material that's being mined. Of course, it's natural material, so it's going to vary a little bit and have not only clay, but quartz and other things in it, carbonaceous matter and things of this nature. So you will see numbers around 850 BTUs per pound per brick, 840 perhaps, and I've computed 872 BTUs per pound. So at least this is a realistic number that we have computed for the bricks. So if you go back for 500 bricks at green weight basis, we should compute 1.21 million BTUs for the process load in order to center the bricks. That's what's required. Okay, now let's deal with the internals in the kill supports, and I computed 794 pounds of kill furniture and bricks. Looks like my spell checker has given me an extra period here in the abbreviation. That happens a lot to me. Specific heat, 0.2 BTUs per pound per degree Fahrenheit, and so you can compute 308,072 BTUs for 500 bricks. So if you're interested in the energy per green brick, there it is, or the energy per fired brick, there it is, if you want to keep the accountants busy. Okay, so we know how much energy is required to heat up everything inside the kiln, but we have to deal with the energy storage in the insulation in the kiln. and we have to deal with the energy heat loss through the sides of the kiln, through the surfaces of the kiln. So here we go, and we've gone to furnace heat losses. We've taken a rectangular shaped furnace. We've added the dimensions of the interior chamber. I noticed in review that I'd used 1800 degrees Fahrenheit here instead of 2000. That's a simple mistake. It really doesn't affect the outcome of this program too much, so I don't think it was worth recalculating. I'm just going to notice that when you do this problem, if you repeat the problem, you should put 2000 in this number right here. And of course, we have said that there are no openings for the purposes of this particular model. Well, of course, you go in, and as you know, you're familiar with these solutions now. When you hit next, you're going to go to the refractory design, and in the top of the furnace, we should have 17 inches of refractory fiber. We have less thickness of refractory fiber in the sidewalls and castable insulation in the hearth. So we should have done all this right. We only had one component in the refractory design: fiber, and castable. And that's why it's shown like this. And then, of course, you hit calculate. Here are the results. So the results have predicted everything about the temperatures and everything about the heat fluxes and heat losses. It's a little easier to see when it's magnified like this. So whatever device you're looking on, I hope you can easily see this. But you can see with 17 inches of insulation in the top, we had a 118 degrees Fahrenheit, the predicted shell temperature here. We had less insulation on the sidewalls, just 8 inches on the sidewalls, and we got up to 154 degrees Fahrenheit. We'd want to check and make sure that that's not going to be above a flesh scalding temperature, human scalding temperature, in case somebody could touch it. But typically, we're going to have more insulation at the top. We remember that heat rises, and so we're going to typically have more heat loss in the top of a furnace. And because of that, the manufacturers are going to increase the thickness of the insulation. Of course, I told you I ran the model at 1800 degrees Fahrenheit instead of 2000. So if you repeat this calculation at 2000, your diagram will show that number right here. Of course, the hearth of the furnace, the bottom of the furnace, is refractory castable, which has a pretty high thermal conductivity, and that's shown by the high temperature on the backside of the bottom of the kiln car. Now, 267 is fine for carbon steel, and so therefore that's fine, and the likelihood of anybody touching the bottom, there's just no clearance for a person to somehow get underneath that, is nil. So we've magnified the furnace heat losses, 41,407, using 1800 degrees Fahrenheit, times 8 hours. So you can see that I get about 0.33 million BTUs necessary for heat up, and heat losses, 331,256. Once I start holding the furnace, all I have to think about is the heat loss times 5 hours for hold. That's 207,035. So the total heat loss is 538,291 BTUs per cycle. Okay, so we've dealt with the heat loss, and we're going to add everything up here. I didn't neglect the storage. It was predicted as 393,000. And so if we add all the energies up, we're going to come up with 2,451,863 BTUs for this process. That included the 872, I guess it was 872 energy per fired brick. add up the kill internals, the heat loss and the heat storage, and total of 1,565 BTUs per brick. Now that's not too bad for a furnace. Of course, just thinking about the significance of the number. Most people in total kills are doing 1,000 BTUs or thereabouts per brick. We're up around 1,500, so that's pretty good. We have a pretty efficient kill. And you can see in the simulation, we're predicting 55.7% of the energy going into making the product, and the other is going into the process to operate. Okay, so we've calculated how much energy with our model. We've projected how much energy would be used in this model. And so if we want to figure out how much gas, we're going to go to the fuel combustion utility, which is in eSolutions. I used average natural gas here, 10% excess air, combustion temperature. This time I used the right temperature, 2000. Really won't make much difference in our comparison. Fuel temperature of 60, meaning room temperature gas. And I'll point out to you that when I run these calculations, I typically will put 1 standard cubic foot per hour as the fuel consumption. Now, I just want the results to be quoted per standard cubic foot. That's the reason I do that. I know you're going to use more gas than that in the process, but I like to put in 1 standard cubic foot per hour. If you were set up eSolutions in metric dimensions, you would probably be using 1 cubic meter per hour or some fraction thereof. I did not set up any ambient conditions of temperature and humidity in this particular model. Of course, that's going to have something to do with the fuel efficiency. Now the output, in brief, once you do the calculation in the fuel combustion utility, it's going to give you an output, and it predicts the composition of the flue gases. It predicts them on a wet weight basis. Okay, CO2, water, sulfur dioxide, oxygen, as nitrogen as N2. Later on, we'll talk about NOx, but it's giving it an N2. The exact same analysis, but on a dry weight basis, when you take the water vapor out, as you do in a lot of pollution measurements, to quote that, you can see the numbers change a little bit because of being a dry weight basis. Of course, we're combusting average natural gas, so we got no sulfur dioxide here. But our available heat is 42.5%. And that's because we're using excess air. The heat available, don't get confused, is 442.854 BTUs per hour. Okay, so if we take that number of BTUs per hour at 1 standard cubic foot per hour, now this is why I put 1 standard cubic foot in that little box in the previous slide, then we're going to have 442.8 BTUs per standard cubic foot, rounded off about 443 BTUs per standard cubic foot. Now, I really haven't computed how much gas yet, so I started with 1 standard cubic foot per hour, and I know the energy that I'm going to get out of that standard cubic foot at 10% excess air for combustion. So then I can calculate the gas that's required. I can calculate it for the preheat of the load, 5,535 standard cubic feet, preheat of the storage energy, preheat the heat loss, the soak, heat loss. Okay, spelling is difficult sometimes for me. And so I add all these up, and I have a total of 7637 BTUs per standard cubic foot. Excuse me, 7637 standard cubic feet of natural gas needed per cycle. Well, that's pretty neat. E-Solutions allows me to experiment with different refractory configurations, different amounts of load. That's what we did in the coils problem. Remember, we stacked the furnace jam full with load, and we looked at the what if question. E-Solutions has also allowed me to calculate how much natural gas, and the accountant's going to like that because that computes into cost. So with one class, I decided we're going to go out in the laboratory and we're going to actually operate the Swindell kiln. Okay, we're not going to go through an entire cycle because we didn't want to waste the natural gas, but we did a test firing. It was made in the kiln, only in the preheat portion of the kiln with no kiln load. No bricks were being fired. It was an empty furnace. And the furnace was fired to 2000 degrees Fahrenheit in 20 hours and immediately shut off. So when we did that, let me correct that a little bit so you can see everything that you need to see. Always amazed at how PowerPoint can jump these things around just a little bit. During a lecture, it doesn't seem like it would, but it did. So these are readings from an instrument called the Kiltel, okay? And the Kiltel gave us the kiln temperature versus time, okay? So here's time on the horizontal axis. Here's temperature on the vertical axis. It's red over here on the left-hand side. Oops, well, I didn't need to hide that from you, did I? Having said that, you can see temperature versus time. We get up here to the peak temperature and we shut the kiln off. We read the gas meter before we started this run. We read the gas meter after we started this run. And we computed the amount of natural gas that we used in this cycle. Interestingly enough, you can see that this Kiltel instrument has an oxygen measuring capability, an oxygen meter with it. And right when we lit the burners off, we're at a pretty high percent of oxygen, certainly over 15% oxygen. So we didn't start out on ratio with this particular kiln. And as we continued firing, the oxygen concentration went down toward 10% or thereabouts when we got up to the peak temperature in 20 hours. But we never got down to 2%. Which we would expect with on ratio combustion. So we learned from this that our kiln used a lot of excess air in the preheat portion of the cycle. Now, when I did the total furnace simulation, this time using the correct temperature of 2000 degrees Fahrenheit, I computed the heat losses and the heat storage. I did it with no openings again, and here's the heat loss and the heat storage and the total BTUs, 1.47 million BTUs, 1,470,940 BTUs. So I can take that and divide it by the BTUs per standard cubic foot of natural gas and predict that I would burn 3,320 standard cubic feet in this kiln simulation. Here's what actually happened. Okay, so we'll move this screen back. Predicted 3,320 standard cubic feet. I measured 2,650 standard cubic feet. So the predicted over predicts the amount actually used by, well, it's 125% of the measured amount. Now, you may say, well, gee, this tells me the model is not very good, but You have to consider that the model is a steady state heat flow model, and when you heat up a furnace, you don't have steady state heat flow conditions. You have transient or changing heat flow conditions. And so we've over predicted some of the heat losses because the kiln is not instantly at 2000 degrees. It starts out at room temperature and begins to heat up. The kiln lining is not instantly at 2000 degrees. We don't have steady state heat flow. So that, I believe, is the major difference in the predicted and the measured. Another way of looking at this might be that the predicted is a decent guideline for you in doing the what if question, as long as you realize that the eSolutions is a steady state heat flow model, and their actual might be a little bit less, could be a little bit less than that. So I am at least pleased with this amount of agreement that we have in eSolutions and the verification experiment. Well, this is my favorite little model to do, and this third model let us compute the heat requirements in the similar way that we've done in the past. We computed the theoretical heat requirement for firing a brick or for firing 500 bricks, and it was at least a reasonable number compared to those that I've seen in engineering literature. Notably, our calculation was based on lab measured values rather than anybody's tabulated values. So this is one way that actual data on your material becomes very, very useful. We calculated the total heat requirement for a furnace cycle. Ultimately, that allowed us to get a predicted cost of fuel or amount of fuel that we would use. And we could predict how much we would use in energy per brick. It's predicted. It's not precise as a measured value, but it's a predicted value. And I believe it's useful because with these predictions, we can do the what if question on different furnace loads, different heating rates, different insulation configurations, and compare these predicted values, making it useful. When we compared the predicted energy requirements to an actual lab furnace cycle and a verification experiment, we found eSolutions to overpredict the gas requirements. And we tried to explain that in terms of limitations of eSolutions. It's a wonderful program for us to use and very useful. Now, I taught the course this way, and I will remind you that when I was taking this course a long time ago, we had to calculate all these things manually. So the combustion course I took when I was a second-year student at the university was nothing like this. We've gone much further with these utilities because we don't have to do manual calculations. That's why I've designed the course this way. I think it's more fun to get to the end result of combustion and actual firing of products. I hope you have felt that way as well. Now in the next class, we're going to look at furnace emissions. That's supposedly unit C of the course in firing defects. Unit C is unfortunately only a one-class unit, so we only have one class to go. I hope you've enjoyed this class.